Hi students, all of you welcome. Welcome to Sunil Engineering Academy. I am Sunil Kumar Bandaro. Students, in this general science physics, we have completed one topic, electricity. You can watch that one in this YouTube channel just by click on the playlist. Now, in this session, we are going to discuss the next topic, magnets and magnetism. Okay, these sessions are useful for all your competitive examinations. Students, please try to share to all your friends and also click on like button. Okay, so now we are going to learn the second topic, very important topic, magnets and magnetism. Okay, magnets and magnetism. So first of all, what is the magnet? So which is considered as a magnet? A magnet is nothing but, in general definition, which can attract iron particle is said to be a magnet. Okay, which attracts iron particles is nothing but you can say magnet. These magnets are generally two types of the magnets. Okay, one is a permanent magnet, second one is the electromagnet. Okay, so magnets are generally permanent magnet and electromagnet. Permanent magnet, electromagnet. So here this how the electromagnet is formed. Whenever a conductor, for example, if you can consider it is a conductor, whenever the current passes through the conductor, it produces the magnetic field around that. It produces the magnetic field around that. That means it will be act as the magnet. So that type of magnet is nothing but you can say electromagnet. Okay. Here, whenever current passes through conductor, magnetic field is developed. Magnetic field developed around that conductor. So it is called as electromagnet. Okay, so this permanent magnet, it is readily available, or we can take any ferromagnetic material and magnetize that one, then it will be act as the permanent magnet. For this, no need of any current. Okay, no need to give current. Okay, so here whenever the current is passing through a conductor, here north pole and south poles are created. Okay, so magnet always have the poles. That poles are always pair in form. Pair means multiples, 2, 4, 6, 8 like that. Single pole may not exist. Okay, so let us take a bar magnet and we can understand each and every point. So up to that, magnet is nothing but which can attract the iron particles or which can produce the magnetic flux. Okay, which can produce the magnetic flux. Magnets are two types, permanent and electromagnet. Electromagnet is nothing but whenever there is a current passing through a conductor, it will be act as the magnet. Whenever there is no current, it may not be act as the magnet. Okay, if the current is zero, electromagnet may not act as magnet. That means as soon as current flowing, then only it will be act as the magnet. Okay, now coming to the next one, let us take a bar magnet. Magnets may be rounded shape, bar, or horseshoe type. So let us take a bar magnet. It is a bar. Okay, so here poles, north and south are poles. Poles are always exist in pair in form. Okay, only multiple poles are exist. Here always the magnetic field lines, note down, the magnetic field lines flows from north pole to south pole like this. North pole to south pole like this. Magnetic field lines outside the bar magnet flow from north pole to south pole. But these magnetic field lines having one important property, they always forms closed loop. Closed loop means anyone start from one point means end at the same point. That is called as a closed loop. So here it starts from north, and closed loop means it also has to be end at the north only. So that means to form a closed loop, inside of a bar magnet, they will flow from south to north. They will flow from south to north. Okay. So note down, magnets have poles north and south. These poles are always pair. Pair means north and south. Pair in form. Example, pair means two multiples, even multiples, 2, 4, 6, 8, like that. Okay. So that means even poles. Poles are always even. Okay. That is like even. Single pole may not exist. Single pole may not exist. That means only south, only north may not exist. Okay, single pole may not exist. For example, if we have a magnet having north and south, if you cut into two parts, then what it will happen? Single pole is not at all exist now, like this. Single pole is not at all exist. So automatically here south pole is created, automatically here north pole is created. Now two new bar magnets are created. Okay, two new bar magnets are created. Note down, if we cut magnet into two parts, then two new magnets are created. Very important point. Okay, so magnet have poles north and south. Poles are always pair in form. Single pole is not at all exist. If you cut into two parts, then two new bar magnets are created. Okay, and the next point, very important point, the magnetic field lines. Magnetic field lines, this is also called as magnetic flux. Very important, magnetic flux. Okay, magnetic field lines always flow from outside of bar magnet north to south. Okay, magnetic field lines always flow in outside of the bar magnet, north to south. Inside of the magnet, inside of bar magnet flow from south to north. Okay, so we have taken here outside north to south, inside south to north. Okay, these magnetic field lines also called as magnetic flux, denoted with phi, always flow from, in case of outside, north to south, inside south to north. That means these magnetic field lines always forms closed loop. These magnetic field lines always form closed loop, and also they never cross each other. They never cross each other and may not intersect. May not intersect. Okay, so if we have another field line, that will be flow same parallelly like this. That means they may not intersect. One may not cross, one may not intersect. Okay, and one more thing. Here we have the field around this now. Here we have the field around this. This is the field around the magnet, correct? This field around the magnet is called as magnetic field. The field around the magnet is called as magnetic field. Okay, so note down the very important point. The field, all these points are important, guys. The field around the magnet in which it has attracting property, in which it has attracting property is called magnetic field. Magnetic field. That means in this field, if you place any one iron particle, it can be attracted. Okay. So the field around the magnet in which it has attracting property is called as magnetic field. Completed? Yes. Now coming to each and every term in this magnets and magnetism. The first one, magnetic field. We have already discussed the magnetic field. Now magnetic flux. Magnetic flux. What is this magnetic flux? So I have already given what is the magnetic flux. The magnetic field lines is nothing but, we can say, magnetic flux. The magnetic field lines of force is called as magnetic flux. Magnetic flux. Okay, denoted with the letter pi. Denoted with the letter pi. And the units are very important now. What are the units of flux? Weber. Or one more unit, Maxwell. Maxwell is the smaller unit. Okay, 1 Weber is equal to 10 power 8 magnetic lines. 10 power 8 magnetic lines of force. That means 1 Weber is equal to 10 power 8 Maxwell. That is the relation. Relation also very important. That means 1 Maxwell is equal to 10 power minus 8 Weber. Reverse also important. Okay. This is the magnetic flux. The magnetic field lines of force is nothing but magnetic flux. Denoted with letter pi. Okay. So it is same like a current in the electric field. Same like a current in the electric field. Now coming to the next one, magnetomotive force. Second definition, second term here, magnetomotive force. Generally it is called as MMF. MMF, magnetomotive force. Okay, so what is this magnetomotive force? It is same like a voltage. If you give the voltage, current is flowing now. So if we have the MMF, then flux is flowing. Okay, it is the force required to move the flux. Force required to move the magnetic flux. The magnetic flux. Okay, and MMF is generally defined as number of turns into current. Number of turns into current. So units are current units ampere, turns unit turn, ampere turn, very important. Ampere turn. Okay. Ampere turn is a unit of magnetomotive force. So in the same way, we have resistance in the electrical. Here reluctance. Reluctance is nothing but which opposes the flow of flux. Reluctance. Next to that, reluctance. Reluctance may be denoted with letter S or dollar. Yes or dollar. Okay. Reluctance is nothing but which opposes the flow of flux. Okay, if the flux want to move, it always opposes. Okay, always there is one opposing quantity is there na. So that is the reluctance, which opposes the flow of flux. Okay, and here generally we have the relation. The relation between MMF, flux, reluctance. Same like Ohm's law here. Okay, Ohm's law is equal to V is equal to I into R. In the place of V, here we have MMF. So MMF is equal to, in the place of current, here we have the flux. Flux into reluctance. Very important. Okay, so from this, reluctance is equal to MMF by flux. MMF is equal to number of turns into current by flux. Then what will be the units? Ampere turn by Weber. Ampere turn per Weber. So this is the unit of reluctance. Now I want to compare the electrical terms with the magnetical terms. Then you will get a clear understanding. Okay, so you have already learned the electrical terms now. Now I am comparing both terms. Then you will get a very good idea. Okay, so but you have to listen carefully. You have to concentrate. Okay, now I am comparing electrical and magnetical terms. Very important. We may not get the question, but from this we can get the idea of both electrical and magnetical. Okay, comparing electrical and magnetical. This table is very important. From this we can give the units of any quantity in the electrical and magnetic. Okay, I know that sitting and watching of these sessions is somewhat like a boring, but these are very important. If we want to get the job, we have to listen, we have to understand, we have to read, and we have to revise. Okay, all these are important. In electrical, we have the fundamental quantity is the current. Units are amps na. Flow of electrons. Here flow of lines, flow of field lines, flux. Here magnetic flux. 5 Weber or Maxwell's. Okay. So if you want to flow the current, here we require voltage. Voltage is also called as, voltage is the net value. If you can consider graph value, that is electromotive force, EMF. Electromotive force, EMF is required to move the current. So EMF volts. Here we require MMF, magnetomotive force, is required to flow the flux. Number of turns into current. The units are ampere turn. Okay. Okay. Now here we have the resistance. Resistance which opposes the flow of current. Okay. Units are ohms. Here in the same place we have reluctance. Reluctance is nothing but which opposes the flow of flux. Okay, so here ampere turn per Weber. Okay, and now here what is the Ohm's law? Relation between voltage, current and resistance. V is equal to I into R. Here what is the Ohm's law? In the place of voltage, here we have the MMF. In the place of current, we have the flux. In the place of resistance, here we have the reluctance. Simple. Got it? So just I am comparing all this. Okay. So note down all this. In the same way here, current density J is equal to current by unit area, ampere per meter square. Very important. This is not given in the electrical. Here current density place, current place flux, magnetic flux density denoted with letter B. Here current place flux, area place area only, flux by unit area. So units are Weber per meter square, and here 1 Weber per meter square is equal to 1 Tesla. Very important. 1 Tesla. So Tesla or Weber per meter square are the important units of magnetic flux density. Magnetic flux density. Okay, completed. So by comparing both, very easy. Here current, here flux. If here voltage, here MMF. Here resistance, here reluctance. Okay. Now one more quantity, very important. Electric field intensity. Electric field intensity is denoted with the letter E. E is equal to voltage by distance or voltage by length. Volt per meter. Volt per meter. Here electric place magnetic. Magnetic field intensity. Here very important thing, another names. It is also called as magnetic field strength. Don't forget another names. Magnetic field strength are also called as magnetization force. Magnetization force. All are same. Here denoted with letter H. Okay. Here H is equal to voltage place. Here MMF na. Okay. Distance place, here length. MMF by length. So MMF, number of turns into current by length. So then what will be the units? Units. Ampere turn by meter. Ampere turn per meter. Okay. ampere turn per meter. So note down this one, ampere turn per meter. Okay, and another name of ampere turn per meter, Oersted. Oersted is also another unit of magnetic field intensity or magnetic field strength or magnetization force. Okay, and we have the relation between B and H. Relation between B and H. B is equal to mu into H. Mu into H. Mu is the permeability. We will discuss about the permeability later. Don't worry. Permeability. Okay. So here units are very, very important. Now coming to the next one. Here we have conductance. Conductance. Conductance G is equal to reciprocal of resistance. Here the same place we have the permeance. Permeance is equal to reciprocal of reluctance. Here units are mho or Siemens. Already we have learned in the electrical now. Here with the permeance, the units are 1 by ampere turn per Weber na. Ampere turn per Weber. So that means here finally we will get Weber per ampere turn. Weber per ampere turn. Okay. So note down all this. Here we have the conductivity. Here we have the conductivity sigma. Conductivity sigma. Sigma is equal to 1 by rho resistivity. Okay. So that means sigma units are 1 by ohm meter. 1 by ohm means mho. Mho per meter. Mho per meter. Here we have permeability. Permeability means it is the ability to permit the flux. It is the ability to permit the magnetic flux. That means if any element having high conductivity, it allows the more current. If any element having high permeability, it allows the more magnetic flux. Okay, units are Henry per meter. Henry per meter. Here mho per meter. Here Henry per meter. Okay. Completed all the terms. They are very, very important, guys. Very, very important. Okay. Now after this we have to discuss the Faraday's laws. Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction. Faraday has given two important laws. First law will give the idea how the EMF will be induced. How the EMF, electromotive force, how the EMF is induced. Induced means produced. Okay. So he has given in this one the first statement, whenever flux linking the coil, changes. Flux linking the coil changes and EMF is induced. The type of EMF is called as statically induced EMF, that is equal to minus N d pi by dt. Okay, so changes means changes with respect to time. D pi by dt differentiation means changes. Here if we have the coil, whenever the flux linking the coil changes, okay, whenever there is a current is flowing through that one, then flux is produces. That flux is changes with respect to time, then EMF is induced. Okay, this type of EMF is example in static devices like a transformer. In transformer, the EMF induced is statically induced EMF. ES means statically induced EMF. Here why we have taken minus? Minus is the Lenz law. Okay. What is this Lenz law? Lenz law is nothing but it opposes the change in flux. Okay. So here whenever the flux is changes and EMF is induced, that induced EMF opposes the change in flux. Okay. Okay. So that is the first statement in the first law. Second statement, whenever magnetic flux cut by the conductor, whenever magnetic flux cut by conductor and EMF is induced, that means if you have a magnetic field, like this, north to south magnetic field lines are flowing. Okay, whenever you take a conductor, if you rotate this conductor, then this conductor cuts the magnetic flux, correct? Whenever we have the magnetic flux like this, if you cut the conductor, that means if you rotate the conductor, this conductor cuts the magnetic flux. Whenever this magnetic flux cut by this conductor and EMF is induced, that EMF is depends upon B, magnetic flux density, L, and length of the conductor, and V, relative velocity. Okay, with how much speed it is moving. BLV sin theta. This is nothing but dynamically induced EMF. Okay, here dynamic, changing, moving particles are there. Okay, so that means in the first law of the Faraday, he has given how the EMF is induced. In the second law, he will given that is how much of induced EMF, that is magnitude of EMF. Okay, in the second law. Okay, so we have to eliminate this. These values are in the second law, we have to give. Okay. Okay, so here example of this second statement, in case of generator it will be happen. Second law will give a magnitude of EMF, that is value of EMF. Okay, as per the first statement, statically induced EMF minus N d pi by dt. Here minus is due to Lenz law. Minus represents Lenz law. Okay, so that means this is the effect, this is the cause. Effect opposes the cause. effect opposes the cause. Okay, and as per the second statement, dynamically induced EMF BLV sin theta. BLV sin theta. Okay, and the next one, motoring principle. Motoring principle or Lorentz force equation. Force equation. As per this Lorentz force equation or motoring principle, whenever a current carrying conductor placed in a magnetic field, if you can consider it is the magnetic field. Okay, whenever a current carrying conductor placed in the magnetic field, if it is a current carrying conductor placed in the magnetic field, then some force will be produced. With that force, the motor is rotating. Okay, so note down the point, then you will get understand. Whenever current carrying conductor placed in a magnetic field, it experiences force. It experiences force. That is nothing but motoring principle. Okay, so in the motor, what is happening? They will take magnetic field and current carrying conductor. Whenever current carrying conductor placed in a magnetic field, it experiences a force. With that force, it is rotating. With that force, it is rotating. That force is equal to, this equation is very important, BIL sin theta. BIL sin theta. Theta is the angle between magnetic field and conductor. Okay, so whenever theta is equal to 90 degrees, that is perpendicular, then what will happen? Angle between the magnetic field and conductor is perpendicular, then sin 90 is equal to 1, that is maximum. So force is equal to BIL, which is said to be a maximum force. Maximum force exists. For example, if theta is equal to 0 degrees, that means both are parallel. Both are parallel. So magnetic field, this magnetic field and this conductor both are in the parallel. Then what is happening? Then there is no cutting of the magnetic flux. No force is exist. So sin 0 is equal to 0. So in this case, that is minimum. Then force produced will be 0. No force exists. Very important question. No force exists in the motor in which are the following cases? That is, whenever magnetic field and conductor are placed in a parallel. Okay, these two are very important. Okay, so whenever we are going to discuss the MCQs, then you will get idea. First of all, try to understand the theory part. It seems to be somewhat of difficult other than science students. If you are science student, it is very easy. Okay, so once again revise all these. Magnet which attracts iron particles, generally permanent and electromagnets we have. Permanent magnet is no need to give the current. Here electromagnet we have to give the current, then only it will be act as the magnet. Okay, bar magnet, poles are always exist in pairing form. Single pole may not exist. Outside north to south, inside south to north. Magnetic flux and units, MMF units, reluctance units, and comparison and their formulas. Formulas are very important. If they have given any numerical, we can easily get the answers if we know the formulas. Faraday's laws, first law and second law. Lorentz force equation or motoring principle. Okay. In the next session, we will discuss Fleming's left hand rule, Fleming's right hand rule, okay, and magnetic materials, dia, para, and ferro. Okay, so we will discuss those in the next session. All of you don't forget to watch the next session also. Okay, and also if you like my effort, please click on like button and also please share the session to all your friends. Okay, if you have not subscribed, please click on subscribe option. If number of students watching is more, then I will also get more interest to take the more sessions. Okay, so please encourage me by sharing to all your friends. Thank you so much, guys.